Now remember, we talked previously about ionic bonding and covalent bonding. In ionic bonding, remember what's formed is a crystal lattice structure in which a positively charged ion is surrounded completely by negatively charged ions, and it creates this gorgeous crystal structure like what you see in NaCl, and that's all that happens. You wouldn't actually draw anything out other than that crystal lattice structure. Now, for covalent bonding, however, for molecular compounds, there are very distinctive shapes that result, and the way that we determine the shape of the molecule and how it actually looks, because it is not a crystal lattice structure like ionic bonding is we actually need to draw out the Lewis dot structure. Now, the Lewis structure can include a single bond, and a single bond, there are 2 electrons that are going to be shared. You can have a double bond in which 2 electron pairs are going to be shared, so that's 4 electrons, or you can have a triple bond in which 3 electron pairs are shared, which would be a total of 6 electrons. Now, how is bond length affected by a single, double, or triple bond? Well, it makes sense that the more bonds there are, the more shared electrons there are, the shorter the bond length is going to be. So this is a key characteristic. If you have a triple bond, you're going to have a much shorter bond length than if you have a single bond. So one of the key concepts that we need to go over when we're talking about covalent bonding and drawing out Lewis structures is talking about electronegativity, because that affects whether a molecule is polar or nonpolar. So the definition of electronegativity is the ability of an atom in a molecule to attract electrons towards itself. Because remember, these atoms are sharing electrons. They're not donating electrons. So if an atom is more electronegative, it's going to be hogging the electron cloud towards itself. And this is key when we actually start drawing these out. So as far as trends are concerned, in order to understand the trend in electronegativity, we need to talk about the trend in size, which you should have learned first year. As you move down the periodic table, the size of an atom, as you can see, increases. Now, the reason why it increases is because you're adding energy levels. Instead of just having the first energy level, number 1 for hydrogen, you've got 2 energy levels for lithium, 3 for sodium, and so you can imagine it getting bigger and bigger with the more energy levels there are in which the electrons are occupied. So as you move down, the atomic size increases because you have more principal energy levels. As you move to the right, however, while you are increasing the number of electrons, you keep the principal energy level the same. It's still the same energy level. What is increasing, though, is the number of protons. So as the number of protons, which are positively charged, increase, the electrons are going to be drawn towards the nucleus, attracted to the nucleus, which means that the atomic size decreases. Well, if you think about the definition of electronegativity, the ability of an atom to attract electrons, the larger an atom is, the less able it is to attract electrons, because the electrons are going to be farther from the nucleus. So, as you move down a group, the atom gets bigger, and therefore the attraction for the electrons decreases, meaning the electronegativity. However, as you move across the periodic table, since the number of protons increases and the size of the atom decreases, the electrons are going to be more attracted, which means the electronegativity is going to increase. So this concept is key when we're talking about bond polarity. Now, the greater the difference in electronegativity between 2 atoms, the more polar their bond is going to be. So this is key because if you think about it, if you have a nonpolar bond, that means that electrons are being shared equally because their electronegativities are about the same, meaning their pull for electrons is about the same. If one atom is more electronegative than the other, then it's going to start hogging those electrons, and if it's so electronegative that it actually steals the electrons from an atom, that's when you end up with an ionic bond. And so that's why we say the difference between ionic and covalent bonding, it's not really distinct, it's a continuum, because if there's no difference in electronegativity, it's a nonpolar bond. If there's a little difference, it's polar. But then if there's a very large difference, you're no longer going to be sharing electrons. Instead, those electrons are going to be stolen, and you're going to have an ionic bond. Now, this concept of bond polarity is key because it helps us to determine dipoles. Now, dipole is created when 2 electrical charges are separated by a distance. And so we're going to be using this when we're drawing out our Lewis dot structure in just one second. So in this class, we are going to learn how to draw Lewis structures that are a lot more complex than what you went over first year chemistry, but I wanted to make sure we are still on the same page regarding how to draw Lewis structures, because you should have learned this, but let's review it just to make sure we're all good. So, I'm going to give you an example. I give you SiH4, silicon tetrahydride, and the first step that you need to do in drawing the Lewis structure is you need to count the number of valence electrons. Well, silicon, if you look at the periodic table, silicon has 4 valence electrons. Hydrogen has 1, but you've got 4 hydrogens, so that's a total of 8 valence electrons. Okay? Your next step is to write the symbols for the atoms to show which atoms are attached to which and connect them with a single bond. So I'm going to take silicon, and since I have 4 hydrogen atoms, I automatically know that this shape is going to be tetrahedral. There are going to be 4 things sticking off of it. And so the way that tetrahedral looks is it looks like this. Okay? So I'm going to draw it like this using the Vesper model. Okay? So this shape, just as a review as I'm going along, this shape is tetrahedral. Okay? And notice now it says complete the octets around all the atoms bonded to the central atom. Well, silicon, every atom wants 8 valence electrons except for hydrogen, which only wants 2. So remember, each line represents 2 valence electrons. So for silicon, it's got 2, 4, 6, 8 already, so it's happy. And hydrogens, they already have 2 from that bond, so we're actually already good. Now, if I needed more, like if this wanted 8, I would add lone pairs of electrons. Now, it says place leftover electrons on the central atom. Well, I don't have any leftovers. I've already used 8 valence electrons, so I'm good to go. And the last step says if there are not enough electrons to give the central atom an octet, try multiple bonds. Well, don't worry, there were enough. This has 8 valence electrons, a perfect octet, so it's good to go. Now, just as a quick review to incorporate the concept of electronegativity and dipoles, if I compare the electronegativity of hydrogen and silicon, I know that there is a difference in electronegativity. I know that silicon is more electronegative than hydrogen. And so silicon is going to be hogging the electrons towards it, and so I represent that with an arrow. Silicon's going to be hogging the electrons towards it, hogging the electrons towards it, and hogging the electrons towards it. Now, it's going to be hogging them, but it's not going to actually steal them from hydrogen. So hydrogen is not going to be positively charged, it's going to be partially positively charged. Partially positively charged, partially positively charged, and partially positively charged, while silicon is partially negatively charged. Now, one concept that we talked about in chemistry, first year chemistry, was, well, is this molecule itself polar or nonpolar? And that's going to be really important when we're talking about intermolecular forces this year. Well, if someone's pushing down, someone's pushing up that way, up that way, silicon's not going to move. And so that's a very basic kind of colloquial way of thinking about it. So what we say is that if it doesn't move, then what we say is that the dipoles cancel. And if the dipoles cancel, then you have a nonpolar molecule. If they don't cancel, then it would be polar. And so that's just the extent to which we're going to talk about it. But when you're drawing these Lewis dot structures, include this information because we're going to expand on it this year. In order to make sure that we're clear on how to draw the Lewis structures, I have 2 more example problems for you. And the first one is carbon monoxide. Okay? So carbon monoxide, the first thing I need to do, if I'm looking at my steps, I need to sum the valence electrons. So carbon has 4 valence electrons, oxygen has 6, so it would be a total of 10 valence electrons. Okay? My next step, I'm going to take my 2 symbols and I'm going to connect them together with a bond to represent sharing electrons. And then I'm going to complete the octet around the central atom. And then, well, I don't really have a central atom here, and so I'm just going to complete the octet around both of them. Well, carbon right now only has 2 and it wants 8. So I'm going to represent the lone pairs of electrons with just a line. So that's 2, 4, 6, 8, 10, 12, 14. So I'm using 14 valence electrons right now in order to make sure that both atoms have a complete octet. So step 4 doesn't apply because I don't have extra electrons. In fact, I don't have enough electrons. I'm only supposed to be using 10, but I'm using 14 right now. So that tells me I'm going to have to use a double or a triple bond. So I'm going to first double bond this. So that represents 4 electrons, so this needs 4 more. And this needs 4 more, so that's 2, 4, 6, 8, 10, 12. I'm still using too many valence electrons, so that tells me I'm going to need a triple bond with just 1 pair of electrons on each of them. Now I'm using 2, 4, 6, 8, 10, and each of them has 8 valence electrons around it. Now, if I draw out the dipole, keep in mind that oxygen is more electronegative than carbon. Therefore, oxygen is going to be partially negatively charged, carbon is going to be partially positively charged, and so oxygen is going to be hogging the electrons towards it. So if I'm trying to decide if this molecule is polar or nonpolar, this molecule is going to be polar because the dipoles do not cancel each other out. Okay, so polar, and I would say dipoles do not cancel. Okay. So let's try one more example. In this example, I give you sulfur difluoride. Okay, so sulfur difluoride. Okay. To count the total number of valence electrons, sulfur has 6 valence electrons, fluorine has 7, but there are 2 fluorines, so that would be a total of 20 valence electrons. So I'm going to draw this. Got fluorine, fluorine. I'm going to make sure everyone's happy. So right now, fluorine only has 2, so I need to add 6 more valence electrons. So I'm going to add 2, 4, 6, 2, 4, 6, and then I'm going to add 2 and 2 there. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and that works out perfectly. Be careful though, because this is not how this molecule actually exists. If I follow the Vesper model, remember what that tells me is that these electrons on the central atom are actually going to repel the fluorine atoms downwards. So you would end up with a shape that looks like this. This is a bent shape. Okay, and then the 2 pairs of electrons on top there. So that's bent. Now keep in mind, fluorine is more electronegative than sulfur. So it would look like that. And so the dipoles do not cancel because you would need something pulling upwards to keep this from moving. So the dipoles do not cancel, and therefore this molecule is polar. Okay? The only other example, if you look back here, this molecule right here, if instead of carbon monoxide, if I had carbon dioxide, when you actually do out the work, carbon dioxide looks like this. Now this shape is linear, which we had assumed it would be for the sulfur difluoride, but it's not. And the reason why it's linear is because there are no lone pairs of electrons on the central atom. So make sure you're careful when you're creating these that you create the correct shape, because that has a large impact on whether or not your molecule is polar or nonpolar.